Yeah, so a couple of words about me. My name is Emanuele. Everyone calls me M, it's easier. And I been in London for the past 8 years, just moved back to Italy. My background is in insurance. I work in innovation for an insurance company. And together with Paolo, we started this group to look at business impacts of quantum London, of quantum computing, quantum technologies.
Right. If I may interrupt, I think I've seen that logo in LinkedIn. The Quantum London is pretty active on LinkedIn.
Yeah, we're on. I will share in a second. We have a slide with some references for our social channels.
Okay.
Take note of those. Yes, we do run a group page on LinkedIn where we do post events that we do together with some news. I will share those in a second.
Sorry.
Yeah, with the introductions. Pietro, do you want to tell a bit about yourself?
Oh, yes, sure. Thank you. My name is Pietro Santagati. I'm Italian and I've been around the globe for a while. And my background is aerospace engineering and mathematical modeling. And in Europe, I've been working in many places. And now I'm based in the Netherlands. And hopefully I will stay in the Netherlands. I'm, I say, quite happy to stay here. And my specialization right now is in software architectures and models. And currently I'm working on applying some modelization techniques to the integrated safety system in the automotive industry.
Okay, cool. Thank you.
My pleasure.
Tom, we know you, but not everyone does know you.
I don't know myself, perhaps. Hey, folks. So, yeah, hi, I'm Tom. I've been a keen follower of the group. I think for a long time. Must be pretty close to its conception. It feels like about a year ago. So my background is in tech startups, AI and ML startups. Been lucky to be partake in some pretty interesting stories for various industries, actually. Right now, I find myself in a lovely fintech startup just by Waterloo called Contexa, which is rather fun. So yeah, really excited to always keep on the edge. Got a history of being involved with some deep tech ventures. So this is really quite exciting for me to see what could be next. And always lovely to speak to you wonderful people.
I'm sure it is. So yeah, going around again, Paolo, I understand is driving, so he can talk. So Paolo's background again is in insurance. He's working in the UK for a big insurance company where he works in operations. I think in his life, he's been trying to, always been curious about new trends and what's coming. So the reason why for funding Quantum London was really around to try and understand, this new technology which is coming our way, what is going to mean for us. Paolo, I hope I've done a good job there. You will tell me later. And finally, Pedro, I see you're on mute. We are just going around the room.
Yes, please. Normally I put myself on mute when the other speak in order to avoid the spurious noise that may come in.
Mm-hmm. Yeah, you can put yourself on mute. Yes, of course.
No, I'm mute. Okay.
Yeah. Pedro, I see you are online. I don't know if you can hear me or not. If you would like to introduce yourself, if you can, otherwise, no worries, we'll just carry on. Oh, all right, yeah, in the chat. Hi, Pedro, yeah. Student joined the last meetup. Okay, thank you. Where are you based, Pedro? Maybe put it in the chat. Portugal, right, thank you. Cool. So for today, we had a couple of, we did try to think of a couple of interesting questions to discuss. And the first one is something that keeps coming our way, and is the difference between quantum computing and quantum technologies. And I know you got Pietro, Rishi, Pedro, you might be experts in the field, but this is something that creates a lot of confusion. So the question is, trying to share our understanding of the difference between quantum computing and quantum technologies. What is the line between the two, and also what are you most interested in, and what do you think is more promising, if that makes sense as a question?
Right. So maybe I could start. I'm
Please,
definitely,
yeah.
I mean, definitely not an expert to take like huge grains of salt. So at least from my understanding, so quantum technology is anything that any technology, any technological thing that you have that can benefit a lot by using extensive quantum mechanics. And right now, maybe it's not even, I mean, it's not too far-fetched to say that current transistors, like current devices at the very current classical computers at the very forefront, like these tunnel FETs and then or these 7 nanometer channel length devices, they also extensively use quantum mechanics. I mean, you're already in that quantum realm there, but we don't consider that to be quantum computing. We still say that it is a classical device, right? Although it's using extensive quantum mechanics.
Yeah.
So at least the way that I see it, the main difference between quantum computing and classical computing is in quantum computing you are using quantum devices to manipulate quantum information.
Yeah.
And then in classical computing, you have like it's still 0 or 1, right? It's not this superposition of 0 and 1.
Yeah.
Do you get that? So I mean, and it's important to say that maybe everybody here knows this, but I mean, at least when I come across these popular tech articles that talk about quantum mechanics, sometimes they say stuff like, yeah, a qubit is 0 and 1 at the same time, and that sort of gives it this computing power, like parallelism. And I mean,
It's an abstraction. It's
yeah,
just an
yeah.
abstraction for the public.
So exactly, and so I would highly recommend anyone who's interested in the field to follow Scott Aronson's blog. And there he's like the best possible I mean like physically realistic thing that you can describe superposition is might be this and might be that. It's not
Richard, I think it would be useful for those who don't know that you write exactly the name of the guy in the chat. So we can...
definitely. Yeah.
I think we have seen a comic recently. We have a WhatsApp group. We shared the comic, which was discussing Iraq.
Right.
Funny,
Oh,
right?
yeah. Maybe we're talking about that. But then the question was, what's quantum technology and quantum computing, right? But so quantum technology is one of the main examples is sensing. So you have devices. I mean, the main issue with quantum computing is that your qubits or your quantum stuff that you work with is highly sensitive. So you have to sort of protect it from environmental influence so that you can work with this quantum information and nothing leaks out, sort of, right? But then the fact that the things are highly sensitive, although a bane in this particular situation, can be used as a boon in another situation where you need high sensitivity. So, for example, like the room that is just in front of me is a squid lab. So it's the superconducting quantum interferometer device, and so that's the most sensitive magnetic field sensors that we have. I mean, the best squids are the most sensitive, not the one right in front of me, maybe. But and you can, I mean, I'm not really sure about the numbers, but you can go to nano Tesla, and that's and people use that to measure the biosignals, right? The signals that comes from the heart, the magnetic signals that come from heart and brain, and I mean, I think there are even devices out there that are like industrially produced, and then it's in hospitals right now that uses this squids, but those are like quantum devices, so they use extensive amount of quantum mechanics and superconductivity and all those things to work, but then they don't do any computation. They don't. So I think at least that's the main difference that I think.
We'll go back to that in just a second. I see someone else has joined us, Mr. Gator. Hello, hi. We're just having an open conversation around a few topics. I don't know if you want to quickly introduce yourself. if you want to unmute yourself or just in the chat, tell us a bit about yourself, what you do, and why you're here. And the question we are discussing is what's the difference between quantum technologies and quantum computing? Because in our group, this comes very often as a matter of confusion. So yes, so trying to summarize what you just said, Rishi, and maybe Pietro or Tom or Pedro, you can add a bit more. So my understanding of your interpretation is, everything which information using quantum mechanics, that's quantum computing, and then processing of that information. Oh, let me try again.
Is it me? Is it just me, or
no? It might be my poor internet connection. Is that any better now?
Yeah.
It's better. That's much better. Yes.
Yeah.
Okay. So I was trying to summarize. So quantum computing is using quantum physics to represent and process information.
Mm-hmm.
Quantum technologies is using quantum physics, quantum mechanics to build stuff. Build technology can be interferometers, can be quantum secure channels, that kind of stuff.
Right.
Is there anything you want to add, Pietro?
Oh yes, there are many things. The introduction of Rishi was very clear and very precise, actually, and very well distinguishing the difference between quantum computing and quantum technology in their own general topics. Let's say, follow up with what Rishi introduced, I would like to mention a practical case about what technology actually offers us now and what have been offering in the last years, and how we have been, say, introduced by the market to new products, in particular in the case of personal computers. And how isn't so difficult to see that we have a quantum device on our desk. So when we started several years ago with the 65 nanometers microprocessors, we gradually moved to the 49 nanometers. What I mean is the gate size of the gate depth in our MOSFET elementary transistor. And as we know, that this enormous number of transistors that works like a set of switch actually process the information that we want the way we want and through programs. As this length, let's say, got smaller and smaller to 32 nanometers, and that enabled the technology to be faster, so working at higher frequency. And at the same time, also to use less energy, so more energy efficient. We experience also some issues related to the reliability of those devices. At such a point, for example, that the forefront of the technology that Intel, for example, offered needed a mathematical coprocessors. And this was the case, for example, of the night corner until 2015. Few years ago, in 2016, Intel came with a beautiful product, which was the night landing, the first processors multi-core that offered an integrated, very small integrated nanoprocessors. Point is that these devices, they solved the issues related to the reliability, to the statistical errors that these machines may do when they used to perform computation. Well, why this error? And the error is due to the fact that statistically, what we perform in a so complex architecture isn't so deterministic. That's the point. And as long as we integrate the scale in the semiconductor technology, what we have currently, some effects takes place. So it isn't just about how we process the information. That is what ideal we want. But actually, what are the external factors that affect or make, let's say, use influence on that way we process the information itself? I'm not talking about the noise. And there are mainly two kinds of noises. that at that integration level counts. One is the blotch noise that I don't get into detail, but basically it's due to the fact that the current that flows through a transistor becomes more and more discrete. I will explain this shortly. And the other one is the thermal effect, also known as a Johnson-Nyquist effect. So the thermal effects on the charges that actually create this perturbation. Well, as long as these integrations came along, 21, 22 nanometers, it was the case of the process like Intel Atom. And we saw those processes. Quantum effect came in. So we had the first effective usage of the quantum mechanics when we had to understand if tunneling actually comes in a build this architecture. It's very important to understand these processes and to understand the reliability of these devices in advance, so on the table, through models. Because deploying a prototype may cost hundreds of millions of dollars, and putting it in productions may cost 3 times that scale. So getting to the market with a product like that at the far front of the innovation, saying customers, now in your server you can perform this kind of operation, you can speed up 20%, 20 times. Well, that's true, but the question that we need to answer now is how reliable these operations are going to be. And we saw that throughout 2010, 2011, that the reliability of those devices wasn't exactly the same that the 32 nanometers, so they were quite less reliable. And the technology improvements through this integration scale toward the 14 nanometers enabled this new technology with a high reliability of the 21. That's why we didn't see that many times the Intel Atom around. The Intel Atom around, we didn't find it in our PCs because it was relatively more expensive if we included technical factors to deploy them in commercial computers on large scale. That's the point. Well, what happens then and now? Now the far front is 5 nanometers. And just a few days ago, IBM released the Power 10. And Power 10 has a 7 nanometers gate between the gate and the oxidized layer. And well, that is a game changer because they realized that at a very reliable way, they can perform with a very energy efficient way operation that traditionally would take longer. And that would enable the deployment of algorithms on a scale that right now would be really prohibitive, at least at high cost.
Here we're still talking about traditional microprocessors, right? So
yes,
basically.
Yes. So what we define with quantum technology, and that is the myth. So quantum technology is a set of tools that combine together that use, or let's say, exploit quantum effect to achieve a goal. Either is a quantum sensing. So when we say classical microprocessor, when we say a semiconductor based, well, it doesn't mean that it isn't quantum. Actually, it is. But we use a quantum effect to simulate the behavior of that machine. However, we use a paradigm to implement a computational model in a classical way. And what paradigm we use? What this machine is? It's the von Neumann machine. That's the big difference between the classical and the quantum. I wouldn't say that in the future some research would say that, or we find out that the semiconductor can be used with some modification for quantum applications. And there is a researcher. There's an Italian guy who is working at Exeter University and then also in Australia, Andrea Morelli. who is very active in this sense.
Yeah.
I want to close this just saying where and how this quantum effect comes in at 7 nanometers to 5 in particular. Is the so-called SET, which is the single electron technology. So the current is detected as a continuous flow of electric charge, but becomes one by one. So the electric field that actually pilots or drives the electron through from the source to the drain, actually in the real current, I mean, is a single electron.
Right.
And exactly, so in the moment we deal with the ACT systems, it's quantum.
Yeah. So if I try to play back to you, so what you were saying, you know, everything is quantum, right? In the end, you know, we live in a quantum reality.
At that scale,
but the difference between the traditional quantum, between the difference between traditional computing and quantum computing is that traditional computing is a von Neumann machine, which means, you know, sequence of steps, right? So you got an algorithm and you got a sequence of steps. And
I would call state. State.
Okay. And then in the quantum computing, you're still using quantum mechanics to represent information, but you have kind of parallel calculations using the quantum physics.
Quantum computing uses a principle which is the superposition of the state, right? So what, in abstract way, people try to explain saying 1 and 0 at the same time.
Yeah.
But
yeah,
it's probably not correct to say parallelly you do calculation.
Exactly.
So for example, if you look at Grover's algorithm, and let's say you have a unsorted array of n entries, right?
Yeah.
I mean, naively, if you would say, okay, find an element in this array, you would need to, in the worst case, you would need to look at each element and then say, yeah, okay, I found it. And so it's an order n computation. But does everyone follow? Yeah. And then, but Grover says that you can do it in order root n. That means you don't have to go through all the elements somehow. And although that does bring in some ideas of parallelism that is happening, it's not exactly like saying you go parallelly look at everything, and then it's mainly that. I mean, the main issue here is that we haven't evolved to understand or comprehend what superposition really is, right? It's math, and we don't really see that happening around us. So we don't have this intuition on what it is. And the best we can sort of say I mean, when I explain to my parents what I'm doing, I tell them, it's just like how a person went through this door and this door at the same time, but I know it's wrong. So it's like, so it depends. Like if I'm explaining it to my relatives or my uncles or aunts at some family party or something, it's fine. If I tell them it's at the same time, it's okay. But then for people who hold more responsibility in the field, like for decision makers and for like people like you, for instance, it's important to, at least I feel that it is important to make that classification. And like Scott Aronson, he's a professor at UT Austin. So he was previously at MIT, and he's a great guy. He's a great communicator, and he has a lot of TED Talks, and his blog itself is a great resource. So I would highly recommend that. It's basically whatever I say would be paraphrasing him and very poorly.
Yeah.
So
yeah. So in terms of our audience, you know, so non-technical people generally, so we try to keep it simple.
Right. Yeah.
So I don't know if Tom, Pedro, or anyone else wants to add anything to this conversation, a specific question. Otherwise, I have another topic we might want to explore together, maybe a slightly less technical. Anyone else want to add a bit around difference between quantum computing and quantum technologies? No. Okay, so let's move on to the next question. So, working in a business environment, something we are trying to understand is when is the right time to start having conversations about quantum technologies? Where should I go to my chief information officer and say, look, this is coming our way, might have a big impact. So is it that, is it time mature to have the kind of conversation? Is it too early? What are your thoughts around this? And have you had any conversations within your companies around these topics? And I will give you also
Maybe Piero, you can start.
what happening within.
Very shortly, I think that when we have ideas and when envisions application of technologies, is always a good moment to start talking about. So there is no reason to delay or postpone discussions, in particular when we talk about research and research transfer to the technological environment. So if we have been talking about quantum in the industry, the answer is yes. But it depends on how we talk about quantum in the industry. Because first of all, it must be clearly understood that serious application on industrial scale of quantum computing is still not achieved. So we have, let's say, experimental platform, several companies, so we don't need to mention the names, but there are several that already have deployed and publicly disclosed their devices for several applications at purely investigation level. But the point is, what can we do with a quantum computer? That is the question. So what should we do with the quantum computer that right now that we can't with the classical one? Okay. The answer to this question is right now there is nothing that we can do with the quantum computer that we can't do with the classical one. That's just to be clear. Solving optimization problems is definitely a very promising ground for quantum computing, and I'm sure that in the short time, I'm not saying that I think of, but I'm sure that in a relatively short time, this kind of problems, so optimization problem, mathematical programming problems in particular, will be a fertile ground for quantum computers where quantum computation will actually take over the classical one. And there are mainly two reasons for that. The first one, and this is when and how people should talk about. So in particular right now. Technology is mature to show that there is a proof of concept in quantum. Technology is too advanced in the classical, let's say, applications of semiconductor technology, based technology, to talk about future. And the reason is the Moore law. If we think about the 7 nanometers that we reached with IBM Power 10 a few days ago, and if you think that now big companies like Google have moved so far since a while to specialized TPUs, to specialized processing unit for machine learning problems, you see that the direction we are taking isn't a general processor that I can deploy in many contexts, like the ones we have on our desk today. But the direction where we are going in the incoming years is a specialized architecture to solve specific problems that can be scalable in a particular market sector or in a particular industry or market segment itself. So the technology will evolve by customer segments and specialized by industry sectors, rather than having a single processor on large scale that you can deploy on your machine and using at 5% of its power. And that's what will happen today with our laptops. This is a good moment to start talking about quantum, as I said before. First, because we have a proof of concept, and many researchers are active in this field. A lot of brilliant minds that are creating solutions not only at the technological level, but also at algorithm level. And that's where I disagree with the many skeptical people that just say the prophecy, quantum will let us. Quantum won't let us. Quantum represents the leap from the classical to the quantum paradigm. The only difference, the substantial difference that we are going to see in the near future, 5 to 10 years, is that instead of having a single processor, let's say, is mass-produced for many domestic products, we will have devices that will be centralized, where you can have access to this expensive technology on premises.
Yeah.
And instead of scaling like we do today in a cloud system, horizontally, or scale out when you need more nodes, we won't have servers to servers to servers to create a data centers, but companies will point to innovation, in particular big firms like IBM, like Google. Now also the incoming Rigetti is doing a great work, like Microsoft as well. They want scale, let's say, or multiplying the numbers of quantum machines to millions. They want.
So they will have to build incrementally better machines. It's not
absolutely,
like
absolutely
a new server and double.
Absolutely, definitely, because those machines are very expensive. So much in comparison, much more expensive than what it costs to develop quantum cloud computing. So the shift from grid computing to cloud computing that we experienced at the ends of the 90s, in the beginning of 2000 toward 2010, that time frame, 10 years, changed completely everything. Grid computing was about the abstractions of the layer. I could add nodes from many operating systems. I could recycle all technology. But it wasn't the right choice because those machines that could be integrated in one single, let's say, data centers was so heterogeneous. The middleware, G-Lite or Globus, they've been abandoned, completely abandoned. Was so heterogeneous that the performances could not be compensated by the amortization of the cost of the devices. That's the point. The cloud offered an alternative, and that's why the cloud now is the software as a service industry, startup industry based on SAS is what 200 billion worldwide. That's why. But the paradigm will be different.
Yeah, that's very interesting. So you're saying you cannot just add more machines. You evolve. You will have to, build better machines. That's quite interesting.
We should redefine what we mean by parallel quantum computing. So in HPC is clear, right? High performance computing, what we mean by parallel. So sometimes people say, I can compute in parallel this, but pay attention. As Rishi pointed out before, what I mean as a parallel calculation in traditional computations means that I have a technology that enables us to perform several computations concurrently. Either is a multi-core, a multi-thread, or multi-node, whatever it is. So I can perform massively several calculations. And there are paradigms. It could be a single instruction, multiple data, SMID or MID, depends. The quantum part, so how can we define a parallel computation? Well, a parallel quantum computing, so it's something that basically isn't even thought right now. So where we are pointing, in my opinion, is in creating a machine that is reliable enough to deploy calculation on it. And just recently, this morning, from IBM, I read an article where they achieved a good result with 27 qubits. a reasonable application of a quantum computing should have at least 300 qubits, which means in a few years we can get there. And the pace is about 25 to 40 qubits per year. Well, where should a company point? Remember that research is very important, but in the end, the market will define the business strategy. So where to go and how to get there.
So,
and yeah, scaling quantum computers isn't effective.
So staying on the same point on when we should start talking to our chief information technology officers. So someone told us recently, quantum is going to have a massive impact on specific areas. So on a lot of areas, it will have little to no impact. In some other specific areas will have a massive impact. We just have an intuition of what those will be, but we don't know exactly. So with that in mind, do you still believe, this is still the right moment to start having?
So yeah, that's what I agree with. Although a lot of what Petro said was news to me too, because I'm still a student, but I do agree with the parts that I understood.
I was a student too.
I am. Right. Yeah, but then I mean, it's always good to have conversations going, right? To start talking and then have people like start talking about quantum, because one really good sign is that a lot of the big companies are already in. I mean, they're all hands in. They have well-established labs and they have huge efforts, and that should at least give us a positive sign that okay, it is happening. It's not like small labs here doing some small stuff, right? And of course, it also I think depends on the field that you're in. If you're in some information technology field or like data transfer or communications, then definitely you should have started. I mean, at least as they say, or when I'm attending talks, from what I hear people say, they say that you should have started talking about it yesterday, because like porting, I mean, although powerful quantum computers might take at least 5 years, 6 years to come into effect, like you can't switch from what you have to what you need to be instantaneously, right? It takes a lot of effort. And then even if you're like going to post quantum classical cryptography or quantum key distribution, this doesn't happen, or from what I hear, it doesn't happen in a span of a year or something. So definitely you need to go start talking about it. But then if you're also in different, in other fields, like maybe optimization, we do know that quantum, I mean, or at least we don't have proofs, like mathematical proofs, but then we have heuristics that strongly point to saying that quantum computers will have an advantage in these algorithms, right? But then I was attending another talk by, I think it was BMW, or where they have like small teams, like automobile industry, where they have small teams working on to see if quantum computers right now in this current present NISQ era can have any impact. And I think the results they had were no, classically it's still better to do, at least right now, right?
Yes.
But then, I mean, the main thing is you can't change, it takes time. And the biggest, I mean, the biggest factor sort of is that it I mean, if your competitor did it, it's almost like this scare factor, I think, that drives this quantum industry. Like if your competitor is already looking at it, then you should definitely look at it, because the advantage may be small, but then it'll I mean, it takes a small time frame, but the leap would be huge, and that's why they call quantum leap, right? So yeah, it's if you're and then it may be it may take too long to play catch up, because
let me just, I will go back to you in a second. So I see Shane has joined us. Hello, hi Shane. We're just having an open conversation around a few topics we are talking about. When is the right time to start engaging with our chief technology officers within our companies? And I don't know, if you want to introduce yourself, feel free. This is a community, so if you want to say a few words about yourself, either with the microphone or in the chat, please do so.
Yeah, hi, this is Shane Rickman. Apologies for being late. So I work for Zapata Computing as a consultant. Basically been in this business 2 or 3 years. Prior to this, worked for Atos in HPC. So my role is to make sure that customers really understand what they can do with quantum computing and what they can't do, and actually solve use cases that are going to bring business value in the next couple of years or 5 years.
Okay, so you are the right one to answer my question there. So the question we are asking is, when is the right time to start having conversation within our businesses around, quantum computing? And Rich, I think the risk there is, people have been bombarded with, blockchain and a lot of things that are going to change the world overnight, and they didn't. So the risk there is, we just start talking about, quantum, and it doesn't materialize, and we make a big noise around it, and we just lose traction. So
Yeah,
I think it's important to catch, the right timing for having this conversation.
definitely. And it happened with AI, right? So there was this AI winter, and then it sort of prospered again. So with the current hype that is being pushed around in quantum, a lot of people predict that sort of the same thing could happen in quantum. But at least I'm betting my career on it. And the main reason for that is because there are actual mathematical proofs that that say that quantum does have an advantage. It's not like heuristics where, yeah, this could be better, but there are like there are mathematical proofs that BQP, or the class of problems that quantum computers can solve, has points that are outside the polynomial hierarchy. That means that is that any classical device can solve, given given all the resources that you have. So and another thing is, I'm not really familiar with blockchain, but and I don't know if there has been like experimental milestones that sort of like prove that, okay, this is coming. But in quantum, we had Google come up with their quantum advantage result like end of last year, and that was like a huge positive reinforcement thing. So I definitely do think it is it's coming, but then it's been coming for a long time now, so I do understand that. Yeah.
So Mr. Gator in the chat is also saying this is way beyond what we're seeing now, so it's still in infant stages. And Shane, what is your take on this matter? Is it too early to start having conversations with our C-suite?
No, so we're already having conversations now. First off, there's 2 things. There's a lack of understanding or experience within the industry generally about how to use quantum technology, how to program it, how to get the best results, and how to optimize things, and so on. And to be honest, a lot of that at the moment sits within universities. And the universities are doing great in terms of education and generating syllabus. I think it's going to be a year or 2 before that flows back out into business, especially the tier 1s, who really need the quantum technology to solve their business problems for the future. So I think now is a good time to focus on academia, which is what we're doing, and also start to work with those tier 1s and set the expectations that, they're not going to solve the problem today. It's going to be in a number of years. But because there's such a shortage of talent, because this is very different than programming HPC, they really want to start now and play with the technology, understand what it can do, and start to build up a small team to do proof of concept and so on, so that when the technology is generally available in 5 years, they can hit the ground running and then basically be ahead of their competitors.
Yeah.
So the time is right now, I think, to do the education.
Mm-hmm.
Yeah,
so if you do people say the same thing, it's a double check. Yeah.
I see your camera is on. You want to add anything?
Oh no, it's been great. Been great listening in. Very informative and very insightful. I think Shane's thought is certainly what I'm seeing. Certainly in the financial space, the tier 1s are investing heavily in proof of concepts. I'm hearing very directly from one particular bank based in Singapore that they're investing in a throwaway basis. They don't expect their investment in a quantum proof of concept to go anywhere. I think what they're trying to establish is where are the gaps in their enterprise infrastructure and where are the gaps in their data, because most of these organizations still have to catch up there. And Rishi, you mentioned there's this competitor fear factor. Honestly, if that's what's driving it, it'll never happen, because the real fear is that competitors may or may not have their data in a slightly less crap way than it currently already is. That's not going to get us to a quantum revolution on its own. So these organizations, bless them, will always be playing catch up. It's part of the joy and why it requires patience to work in these industries, and you have to be a little bit sort of temper your expectations at every corner. But I think that's going to drive proof of concepts, though, because you can spend this tier 1 is spending 5 mil with a quantum tech startup to run a simulation. Basically, there'll be no actual quantum hardware involved, but it's an interesting exercise. It's almost like a mock exercise to find out actually how far they are. And the reality is, most of this particular part of what this institution does is business rule driven. So you can imagine, if you have a bunch of discrete business rules which are highly classical and non-probabilistic, how on earth do you get towards a quantum value add? It's just we're speaking compatible languages here. One thing I would say is I appreciate that. I know I say this every single time, that there are some mathematical proofs, or there are some very nice thought experiments we can do to prove that there is a quantum advantage, but as against a classical discrete algorithm, right?
Mm-hmm.
So quantum algorithms are not, unless I missed some massive news here, they're not going to break out of polynomial time completeness, and they're going to give us a quadratic speed up as with Grover, but they're not going to give us a absolutely break the boundaries of computer science as we know it speed up. And let's remember that they actually, if you compare even the hypothetical results we'll be able to achieve on a machine with a quantum volume of what was the example, 300 qubits there, they will only be competitive with a statistical approximation algorithm based on learning. So the comparison between a quantum algorithm and a classical algorithm is often quite unfair, because probably some clever person at Google will have an amazing deep learning model that will be able to produce a similar result approximately, and it might be overfitted in some ways, and it will be rough around the edges, and it won't be as accurate. But this is kind of roughly what I'm seeing. Sometimes I feel like the game is a bit stacked, but that's my controversial statement for the night. And on that note, I might go quiet and be shot down and taken to pieces by our experts here. That might be too controversial. I don't know.
But at the same time, I could argue we explore fully what the potential of algorithms within the quantum computing are. Maybe there's a lot there to be discovered as well, right?
Yes, I mean, the person that can, it's like that. It goes back to, in very, very non-technical speak, it goes back to that communications barrier. That's not just about people talking about whether it's a qubit being 1 and 0 at the same time. It's about the fact that language of 1 and 0 at the same time, and more to the point, that classical language permeates these industries completely. At every juncture, every business rule, every decision process, every criteria to have explainable models, every the way the data is stored. We mentioned Grover's algorithm earlier on. That works when the data is entangled in a load of quantum registers. By the way, it will be in databases forever. It's never not going to be on disk, and so the question about the applicability of that algorithm in the first place will come up. So this is why this is interesting. I think we should try to make mistakes now. This is the era where we cock up, if you can excuse my language. Sorry, I know we're being recorded. This is the era where we mess up. We run some POCs, and we realize that the current state of what we think use cases for quantum are utterly incompatible. But we have to get there, because we need then these tier 1 organizations, these organizations with amazing data assets, to go away and fix the way they work. And I'm increasingly, having been on this wonderful group, I used to think that would be 3 years. I now think it's more like 5 to 10 years. But we have to do it. Someone has to do it.
Yeah. I don't know. Personally, I think it's a bit too early to start having that kind of conversations within our companies. I tried, and the answer is, well, it's interesting. It's fascinating how we understand this is coming our way. It's changing things, but when, first of all, and today the answer to the question is, how should I care today? I think that's still the question at the moment. So personally, my experience saying it's a bit too early to start having. It's great to have these conversations, like the conversation we're trying to drive, but for our C-suite, personally, I think is still a bit early. I don't know if anyone else has any thoughts about this.
Yeah, I mean, again, maybe I should have started with the disclaimer that I have zero business knowledge and I'm purely been living inside the walls of like academia. So yeah, but yeah, please take that with that. And I totally agree that with what Tom said, like we should make mistakes, and right now is the time we make mistakes. And also this I mean, a lot of times these quantum machine learning and these things start popping up everywhere, right? And most of the times it's just you mix buzzwords together, and we don't even know that if quantum computing will, or at least we don't have provable results that show that you get an advantage. All the advantage that you usually get is polynomial, like Tom said, and it's not huge. But again, people are still interested in quantum computing, I think, also mainly because of simulating quantum chemistry, right? And that, I think, is something that is possibly a very interesting area that quantum computing can help. I mean, at least that's my understanding. And yeah, so again, I think we still also there's this expectation of quantum versus classical. Classical computing has had decades of research, and then all these developments that took so damn long to bring about the results that it has now, like deep learning and all these. You have TPUs and GPUs and so on, but quantum is just like a baby just crawling right now, and then it's asked to be on a marathon with yeah, so it's with an ostrich maybe, but yeah.
So
but
Rishi, you make a good point, right? So my thoughts about this for the future are that, you know, the mystique about quantum will disappear. It will become another black box, which is a compute box. And
right.
You know, in maybe 5 years' time, customers will submit a job into the grey box. The grey box will figure out, can I solve this problem in an HPC environment? And if I can, I'm going to divert it to that environment. Or is this too complex, or it's going to take too long in HPC? I'll divert it to a quantum accelerator. And the customer at the end won't care how his job's run. He just wants the results back in a specific period of time. He doesn't care whether it's done on HPC or quantum. So I think, you know, some of the intelligence will start to shift into the environment to make decisions on where is best to do this computing and how to do it. And I think probably, you know, the big guys like Microsoft, AWS, Amazon, etc., are going to have this hybrid environment, which is a compute environment, which is going to be a mixture of traditional HPC and also quantum technologies. And I think that's going to drive the industry, to be honest, in the next 5 years or so, before people then start to look at premise.
I fully agree. I just want to add to what Shane pointed out right now, that IBM already has this tool. This is IBM Q optimization. And it pre-processes the script and the entity of the computation and evaluates if these computations should be better addressed to a classical computing infrastructures or to a quantum one.
I know we are a bit out of time, but I do have another question if you guys are happy to stay a little longer. And the question is, so what kind of model do you see happening? I'm referring to, okay, we got these big companies having their machines, and we discussed earlier that we probably think is going to be software as a service kind of model. So we will not have a quantum computer in our company. We'll just have access to AWS or IBM's quantum computing power. So how do you see this happening? Will there be like kind of partnerships at this stage, more of proof of concepts where we talk to AWS and the likes and we build proof of concept together? Do you see a model where we have system integrators or people developing quantum algorithms and then using Google or IBM just to do the compute? What kind of model do you see happening here? I hope my question was clear.
Yes, it was very clear. This is a equation that is I don't know if we have time for this, but it's quite complex. What you are talking about, how the market is going to shape around quantum technologies and quantum computing services. So we discussed before how we abandoned gradually the grid computing paradigm to embrace the cloud computing, and how the cloud computing today is actually offering a completely different new paradigm, both in technology and at business provider. When you offer to the public, so let's, I try to synthesize, to concise as much as possible in 1 minute. And so I'm very likely I will be not precise as these answers should deserve. So when we say quantum computing is faster, and that is the promise, right? We also need to consider how much is going to cost this speed up, because in the end, the end consumer is going to pay for. Let's assume that still the cost is affordable compared with the revenue that this customer is expected to get from the deployment of his own service to a quantum platform. The point is then, if I don't have enough services, so if the infrastructures that I deploy to match the market demand doesn't cover the demand itself, what is going to happen is that I cannot scale my business, and from economy, let's say from an economy of scale, the market topology will become an economy of demand, which changes completely everything. At that point, if this happens, quantum technology or quantum computing wouldn't be so effective like cloud computing is today. So scaling horizontally, like today cloud offers, giving us the illusion that we have infinity resources with multi-region, could be not possible with quantum. And that is the strategic part. So before thinking what kind of paradigm we are going to face, we need to think about what kind of market we are going to create. Because we have to remember that we need to think differently than we could do from the perspective of the academia or the research institute. The market shape the product, the demand, and we shape our business model based on the product or service we want to provide.
Yeah.
Extremely important.
If the market is like that, that's fascinating, because you can see actually quantum taking off in an area where the compute that's being asked of it is commoditized in a certain way. Rishi, you mentioned simulation. I love simulation. So you can see in a world there where actually, say you want to do if there's such a thing as well, there is, I think, a quantum Monte Carlo simulation. So say you're doing a Monte Carlo simulation or something. Paolo's not here, but let's say it's hurricanes for his classic example. You're doing a simulation of hurricanes. I can see that you would require a simulation with a certain burn-in and a certain number of instances, and actually you'd commoditize that compute. So if you could afford some time on a quantum computer, some of that will be done on a quantum computer. Otherwise, the rest of it might be done using a classical computer or using an approximation method or a TPU or something, and it would take a bit longer. I think if it's going to become a real demand-based market, I can see actually if we can conceptualize, focus on problems which are accelerated by quantum computing, but also can be completed using classical methods, then that commoditization is possible. And so I can see at a problem level a kind of cloud-based. I like that. I can see someone dialing into a simulation service where 10% of their simulation might be on a quantum computer, depending on resource and availability. That would be really fun.
That's right.
So Tom, that's already happening. So without
Wow.
giving any secrets away, we're working with the university that's actually doing Monte Carlo simulation on a simulated quantum machine, and then accessing occasionally a real quantum machine to actually run it. It's for the finance segment.
I would not be surprised. I'm really interested to see where that goes.
Yes.
That could be the first big disruptive way to go to market, because simulation has that wonderful thing that it doesn't require an organization to have their data in the right place. You can add value immediately. So yeah, that would be really fascinating. It'd be really fascinating to see if topics like synthetic data, which touch on simulation, take off. But again, whether there's a market for synthetic data startups is a big question, looking at hazy and synthetic with a Q. Whether those players can actually stand on their own 2 feet without quantum computing is interesting in itself. So there's a market question there as well. Oh, could be so fun. Fast forward a year.
I think the other thing that's going to happen is we're going to see generalized adversarial networks comprising of traditional HPC and AI working in tandem with quantum machines to actually, if you like, be adversarial with each other. So they're actually finding the best solutions from an overall perspective and utilizing the best of the technologies at the same time.
That's a fascinating idea. So teacher student in machine learning, but where the teacher is potentially an expensive quantum machine. So you're saving costs.
Exactly right.
Yeah.
So,
That's really good
we
idea.
have people already thinking about that. Absolutely.
I'll nick that idea then. Nah,
Only
I'm
if you
kidding.
reference
I'm
me.
kidding. We're under friend A. We're friend A here, I think. There we go.
Right. I don't know. We are 15 minutes over, so I will stop it here if you want to do that. And just as a reminder, we got a webinar coming on the 9th of September with Paul Guthrie and Marco Paini. They were leaders at QX branch, which was recently sold to Rigetti. So we're hoping to get some insights from them, which will be interesting conversation. It will be more into webinar format, so them telling us about their story and with questions asked in the chat. So if you are around, have a look at that. Also, I promised at the start and then I forgot to share our social stuff or channels. So I have them on the screen now. Maybe you should see them on the right hand side. These are all our channels. Maybe you want to take a screenshot, or I will also send them in an email. We have, Parcel is a great way to share with the community interesting articles you come across. If you want an account on there, just let us know. Is an easy way. You find something interesting you want to share with the community, it's one click and it builds a good library of interesting stuff for people to read. And clearly we have the meetup, which you probably come across because you're here. And I think Rishi, at the start, you were mentioning the quantum page. We do have one on LinkedIn. So these are all the links. I will share them in an email. And yeah, thank you very much for joining us today. It was, really interesting conversation for me.
Yeah.
Thank you.
And I also have put my LinkedIn ID address in the chat. So if anybody interested in connecting, then please.
Yeah, absolutely.
Yeah,
thank
I would love to.
Great stuff. It's amazing fun as ever. I can't wait to do this when it's safe to do so and people are comfortable to do this in the Vintry again or something. That would be really great.
I was having a beer in the meantime, This was done in a pub, so that's the right.
I totally agree with that. This has been a fascinating conversation. I'm sorry I joined late. I was on a business call, but absolutely, doing this once a month or something and then face to face, I think is incredible. I think there's a lot of knowledge in this group.
Yeah.
Right. Yeah.
Also, if you have any speakers, people you would like to hear from, just let me or Paolo know. We will approach them. And so far, we've been relatively lucky. We had some good people joining us for webinars. So if you can think of anyone you would like to hear from, just give us the name and we'll approach them and organize something.
I know I owe you a reach out to my insurer. My insurer friend, I will do that. Cool.
Yeah, we got a quite good pipeline. So, but yeah.
Really? Wow.
Yes. Please, let us know. Okay.
Right.
Cool. Thanks everyone again.
Lovely.
Great to talk with you.
Bye.
Have a nice evening.
Okay,
Take care.
Take care.
Bye.